looking at Cramers rule application in isolated model, we first looked at what essentially Cramers rule is. Then we looked at how we can use the Cramers rule in the ISLM model to determine equilibrium values of output and interest rate without having to use substitution. So we looked at this as an alternative method to substitution. Now we want to look at how we can use Cramer's rule to determine impact on equilibrium output and interest rate due to changes in exogenous variables or intercept parameters in ISLM model without even having to find the equilibrium values. So if we're only interested in the multipliers, then we can use Cramer's rule to determine these multipliers without first having to find the equilibrium values and then using those to find multipliers. For this, we'll consider the following ISLM model given. Now, moving forward. Now, suppose we want to determine the impact of changes in government spending and real money supply on equilibrium values of output and interest rate. Now, one way to do this is that you first find the equilibrium values of output and interest rate, and then you can take the derivative of equilibrium y with respect to g, and then with respect to real money supply. Similarly, take derivative of equilibrium I with respect to g and then with respect to real money supply, right? So one way if you want to find these multipliers is to first find the equilibrium values of output and interest rate and take the derivatives then with respect to whatever exogenous variable that you want to find its multiplier with respect to. We want to now see how we can instead find these multipliers without even having to find equilibrium output and interest rate using Cramer's rule. So one approach is obviously you can find the equilibrium values and then take relevant derivatives to find multipliers. The other approach is that you can use Cramer's rule to find these multipliers without having to first find equilibrium y and I. So so over here the application of Cramer's rule is that if you're not interested in the equilibrium values and you only want the multipliers, so Cramer's rule allows you to directly find the multipliers without having to find the equilibrium values first. So let's see how will we use Cramer's rule. Now, step one is going to be totally differentiate your ISLM model. What this means is that you calculate the differential on both sides of IS and then you calculate the total differential on both sides of LM. And but when I say here, totally differentiate the ISLM model, this means that instead of looking at the levels, e.g. y, we look at the changes dy. So let's go back to the ISLM model we looked at. So I want to totally differentiate this model, which means that instead of looking at level y, we want to look at the change dy. Instead of looking at t, we want to look at dt. Instead of looking at g, we want to look at dg. Instead of looking at m by b, we want to look at dm by b. Right? Instead of looking at I, we want to look at di, right? So basically, we want to totally differentiate this ISLM model where instead of focusing on the levels, we want to focus on the changes. And here when you totally differentiate this, so here the differential will be dy. This will become dc naught plus c1 dy minus c1 dt. Just keep in mind, in the case for differentials like derivatives, constant multiples can come outside, right? So c1 is a constant multiple, it can come outside of the differential. And differential sum is also somewhat differential. So like derivatives, for differentials, constant multiples can come outside and it can go inside solutions. When we're taking the total differential on the right-hand side, we are applying that. Okay, we know, okay, differential sum is sum of differentials and constant multiples can come out, right? So this will become plus db naught plus b1 dy because constant multiple b1 can come out, minus b2 di because the constant multiple b2 can come out, plus dg. dm by p is equal to dd naught plus d1 dy, again the constant multiple d1 can come out, minus d2 di, again the constant multiple d2 can come out. So the first step when you want to determine multipliers is to totally differentiate your ISLM model. When instead of focusing on levels like y, we want to focus on changes like dy. And in this case, like keep in mind, like derivatives, differentials can go inside summations and constant multiples can come outside. Right, so we're totally differentiated our ISLM model. Now we will interpret these two equations as a new equation system where we have two new endogenous variables, the differentials dy and di. Initially our endogenous variables were y and I, but we're interpreting this as a new equation system where we have two new endogenous variables, the differentials of our original endogenous variables du and di. Now the changes in the exogenous variables are our new exogenous variables, right? So dg is an exogenous variable, dt is an exogenous variable, and so on, right? Okay. I'm sorry. So let's move forward. So the first step was we totally differentiate the ISLM model, right? Now the second step is going to be we're going to rearrange it so that our endogenous variables, where we know our new endogenous variables are the differentials dy and di, appear on the left hand side, and the differentials of our exogenous variables and intercept parameters on the right hand side. Equation. So first step is you totally differentiate your ISLM model so that instead of levels now you're looking at changes. The next step is you ensure that your endogenous variables, which in this case in dy and di are on the left hand side, because here see you have dy on the left hand side as well as on the right hand side. Here dy and di on the right hand side. So you want to rearrange the equation so that your endogenous variables, which are now dy and di, they appear on the left-hand side, and the differentials of exogenous variables and intercept parameters appears on the right-hand side of each equation. So here this would be dc naught, here it would be minus cu1 dt, db naught, dg, and here it would be dm by b and dd naught, right? So we rearrange. The next step is to rearrange it. And here we've rearranged it so that our endogenous variables dy and di we can see are on the left-hand side of each equation. And the differentials of our exogenous variables tg and m by p and the differentials of our intercept parameters c naught, d naught, b naught appear on the right-hand side of each equation. Now the next step is going to be we're going to write the model in matrix form. Now let's recall here, when we were using Cramer's rule to solve for equilibrium values of output and intrust rate, the matrix form we wanted to write a model was in the form Ax is equal to B, where in X we had our endogenous variables, A was a matrix of the coefficients, and B was everything on the right hand side. But when we're finding multipliers, what we can do is we could still write it in the form Ax is equal to B and solve it as well, but we can all do it in a different way as well. Right? So even now, when we're finding multipliers, we could still use Cramer's rule to find these multipliers while writing it in the form Ax is equal to B. That's still possible. You could do it that way. There's another way you could do this where when you want to find multipliers, you can instead write it in the matrix form Ax is equal to CD. But X is your column vector of your endogenous variables, which in this case are dy and di, right? We know X is a column vector of endogenous variables. Endogenous variables are dy and di, which we've written over here. A is the matrix of coefficients of our endogenous variables like before, right? So Ax is the same thing. X is still our column vector of endogenous variables. A is a coefficient, right? So if we go back, over here we know the coefficient of dy is 1 minus c1 minus p1. So here we have written 1 minus c1 minus p1. And in the first equation, we know the coefficient of di is b2. So over here, see, we have written b2 has the coefficient of di. In the second equation, we know let's look at what the coefficient of dy is. In the second equation, notice the coefficient of dy is d1 and the coefficient of di is minus d2. So over here also we have written d1 as the coefficient of dy in second equation and minus d2 as the coefficient of di in second equation, right? So Ax is still the same. X is your column vector of endogenous variables, which in this case are dy and di, and A is the matrix of their coefficients. Now, instead of B, what we have is we are split B into C and D matrix, right? Where D is what? D is a column vector of the differentials of exogenous variables and intercept parameters, and C includes their coefficients, right? So now instead of using B, what we've written CD, where D is a column vector of your differentials of exogenous variables and intercept parameters, and C is the matrix of their coefficients. Now, in this case, you have the option. You can put differentials of all exogenous variables and parameters in D and the coefficients in C. So I could add in D every single exogenous variable and intercept parameter on the right hand side, right? So we could add dc naught, we could add dt, we could add db naught, we could add dg, dm by p, dd naught, right? So we could add all the all the differentials of exogenous variables and intercept parameters that we see on the right hand side, we can add them in D and the coefficients in C. Or we have an option here that we can only put the differentials of required exogenous variables and intercept parameters in D and the respective coefficients in C. Instead of adding differentials of all exogenous variables and intercept parameters on the right hand side, when you're finding multipliers, you have the option that you can only put differentials of those exogenous variables and intercept parameters that you need. In this case, we're interested in changes in G and M, real money supply. So we want to see that when government spending and real money supply changes, how does that affect equilibrium by and I? So since we're only interested in changes in G and M by P, so in column D, we can only put the differentials of the exogenous variables and intercept parameters we're interested in. So instead of putting all the differentials that are on the left hand, on the right hand side, we can just put the ones that are required, which are dg and dm by p, right? So you have this option when you're finding multipliers, you have the option that in this matrix D, you can just put the required differentials, the required exogenous variables and intercept parameters, right? So I'll just put dg and dm by p here. And in column C, you'll put the coefficients, right? So let's go back and let's see. In the first equation, the coefficient of dg is 1 and the coefficient of m by p is 0. There's no m by p here, so the coefficient is 0, right? So we've written 1, 0 here. And in the second equation, if we go back, the coefficient of dg is 0 because there's no dg here, and the coefficient of m by p is 1. So the coefficient of dg is 0 and the coefficient of dm by p is 1, right? So here when we're writing it in matrix form, instead of using ax is equal to b, we're looking at how we can use ax is equal to cd. The good thing about using this form is here you have the option that in D, you can only put the differentials of those exogenous variables and intercept parameters that are required, in this case, dg and dny. So just recall over here that so we looked at when using Cramers rule to solve for equilibrium finite, we used the matrix form Ax is equal to B. To find multipliers, we have used the matrix form Ax is equal to CD. When you're using Cramer's rule to solve for equilibrium output and interest rate, we have to put everything on right hand side in B. But when you're using the matrix form Ax is equal to CD to find multipliers, you can only put what's required in C and D instead of putting everything. So this makes the calculations a bit less tedious.